Hello my scholars, welcome to my school YouTube channel. My name is Emmanuel and in today's video we'll be tackling JAMB CBT past question for chemistry in the year 2006. Please don't go anywhere, stick around and we'll be right back. Yeah, welcome back to my school YouTube channel. In today's video, we'll be tackling question number 1 to number 25. Now, let's get down to question number 1. The raw materials used for the smelting of iron ore in a furnace is what? You must understand, first of all, that there are 3 major raw materials we have in the smelting of iron. Number 1, we have iron ore, which will contain the magnetite or the hematite. Okay. Number 2, we have the limestone, which is your calcium carbonate. And number 3, we have coke, which contains your carbon, okay, from the fossil fuel. So what we have, the major thing we have, the iron ore, which is the hematite, usually should contain the iron ore that we mean to what? To extract from, okay. And in addition to that, we have calcium carbonate, which is the limestone. The limestone acts as the fluxing agent, okay, helping in what? In removing at high temperature. It will help in removing the impurities that is present in the ore, okay. And then thirdly, we have the coke, which is the what? The source of carbon from the fossil fuel. So those 3 are what we have. So if you look at the options we have calcium sulfate, okay, which is not one of the ones I just mentioned. When we talk about the iron ore, we are talking about the iron oxide, okay. That's the iron ore. So we don't have iron ore here. We have option B, we have calcium carbonate, which is a limestone, which was one of the ones we mentioned. And then number 3, we have copper sulfate, which I didn't mention that, okay. And then we have zinc nitrate. So among these options now, we don't have iron ore here, which is Fe2O3, okay. And then H2O. We don't have carbon here, which is your coke, but we have calcium carbonate. So the raw materials used for the smelting of iron ore in a furnace is no other than calcium carbonate. So the correct answer is option B. Now let's move on to question number 2. On heating, which of the following compounds will decompose to the free metal nitrogen 4 oxide and oxygen? So among these options now, which one will give us metal, okay, when you decompose, when you apply it to heat, okay, will give us a free metal? We have nitrogen 4 oxide, which is your NO2, and then we have what? Oxygen. So which means in all of this, to solve this, we need to write a chemical equation to show the decomposition process for all of this. So the first one is calcium nitrate. Let's move to the board. Let's move to the board. We have calcium nitrate, NO3 2, okay, that's the first. Then for the second, we have copper nitrate, NO3, that is 2. Then the third one, we have silver nitrate, NO3. And then the fourth one, we have sodium nitrate. So we have this. So let's write the equation. So you have this, then we have a triangle here. When we see delta, it means it is being applied, okay? So when we decompose this, we are going to have calcium oxide, okay, plus we have NO2. Then plus we have oxygen, okay. So if we balance that equation, we have 2 here, because we have 2 here. Then sodium here, nitrogen will be 4 here. Okay, I think this balance 4 nitrogen, 4. This is 2 and 2. That's 4. Calcium is here. So you can just balance the equation. So we have this. When we decompose copper nitrate, we are going to have something more like this. So we have copper oxide, we have NO2. And then we have oxygen also. So if you balance it, you have 2 here, 2 of this here, then we have 4 here, okay. So let's look at the third option, silver nitrate. If you apply it to silver nitrate, we shall have silver, okay. Then we'll have NO2, yes. Then we have oxygen. You can just check the equation to see if the equation is balanced, okay. So we have, this is NO2, so we have 2 here. We have 2 here, so this is 6 here, so this is 2 here, so we have 2 here also. So that's the equation. And then lastly, we have sodium nitrate. So sodium nitrate, we are going to have sodium nitrite, NO2, yes, plus oxygen. Okay, that's what we're going to have. So here is 2, we have 2 here. So this is 4, this is 6. Okay, so we have a 2 here also, sodium here. So the equation is balanced. We have this. So the question says, on heating, which of the following will decompose to the free metal? So if you look at option A, it says free metal, nitrogen oxide, and oxygen. There's nitrogen oxide here, there's oxygen here, but this is not a free metal. This is calcium oxide. So option A is eliminated. Option B, we have nitrogen oxide, we have sodium, we have oxygen, but this is not a free metal. Okay, so this also is eliminated. Silver nitrate, for this we have nitrogen oxide, yes, we have oxygen, yes, and then we have silver, which is what? A free metal. So this is correct. Look at this, we have only oxygen, we don't have nitrogen oxide, and we don't have a free metal. So this always, so option C is the correct. Let's move on to the screen. We have that. So among all of this one, silver nitrate happens to be the one that is going to give us a free metal, which is silver. Will give us nitrogen oxide, which is NO2, and give us oxygen also, which are the 3 products that we can have there. So the correct answer is option C. Question number 3. The group 1A metals are not found free in nature because they are what? Don't forget that group 1A metals are the alkali metals. Okay, they are in group 1, alkali metals, and then we talk about lithium. Of course, hydrogen is there, of course, because it also have 1 electron in the outermost shell. So that is why it is grouped under the group 1A element. So we have lithium, we have sodium, we have potassium, and so on and so forth. So we have them for the first 20 elements. So these are not found, they are not found free in nature. Don't forget that alkali metals are rich in electron. Okay, they have 1 electron in their outermost shell. That is why the ionic form is always positive. So you can see Li, lithium, positive. You only see sodium, Na, positive. You see potassium, K, positive. So which means that they have 1 electron in the outermost shell. So by the time they will be always ready to do what? To give out that 1 electron they have in the outermost shell, so that they can, you know, observe the octet rule, okay, and the stability rule, so that they can become stable. So what do they need to do? They would need a non-metal that is deficient of an electron to give. So that's why you see them more like in bonding. They get involved in bonding, and then they exist together in ionic bonding, okay, because they need to what? Give out that electron in the outermost shell, so they can lose that electron in the outermost shell and become stable, okay, like every other element in group O element. So they are so reactive, very reactive. So the reason they are not found free in nature is because option A says they are very reactive and unstable. Yes, they are very reactive, okay, and they are unstable because they want to always give out that electron so that they can become stabilized. Correct. Option B says they are malleable and ductile. Of course, they are metals, they are malleable, they are ductile, but that does not confer on them the reason why they are not found free in nature. So that is not correct. Option C says have high melting and boiling point. Of course, we know that metals have high melting point and high boiling point, but that is not the reason why they are not found free. And option C says conduct heat and electricity. Of course, that is another characteristic of metals. They conduct heat and electricity, but that is not the reason why they are not found free in nature. The reason they are not found free in nature is because they are very reactive. Of course, they are the most reactive metals, okay, that we have there in the periodic table, and they are stable. So the correct answer is option A. Question number 4. Carbon exists naturally in the combined state as what? So which means that in their combined states, okay, where can you find carbon? Okay, there are 3 material substances in which you can find carbon existing naturally. The first one is in fossil fuel, that's in your petroleum, that's in crude oil. We have carbon in the combined state there, of course, with hydrogen and other compounds. We have them present in the wood, okay, the wood. That's why when you burn the firewood, you get it in the charcoal, okay. We have carbon there, present there. And number 3, it is in the natural gases. So those are the 3 resources where you can find carbon existing natural in the combined state. We talk about petroleum, we talk about wood, and then we talk about natural gas. So let's look at the options we have. Graphite, of course, graphite is an allotrope. Graphite and diamond are allotropes of what? Of carbon, okay, but not in the what? In the combined state. So this is not correct. This is not correct. And coal, well, coal is a type of charcoal, like we can have it, okay, but don't forget that coal, the charcoal came from something, okay, came from the wood. So the major source of charcoal is what? Is the wood. So we talked about petroleum, we don't have petroleum here. We talked about natural gases, we don't have natural gases. We talk about wood. So we have wood here in the option. So we go for option D. The correct answer is option D. Question 5. The efficiency of a solid catalyst to increase reaction rates depends on its what? When we talk about efficiency of a solid catalyst, how efficient, how reactive, okay, can that solid catalyst be if it is what? Undergoing a chemical reaction? Option A says surface area. Now, when we talk about surface area, of course, we are talking about what? Solid catalyst. Now, surface area has to do with the part of the solid catalyst that is exposed, okay, that is open to what? To reaction, to substances that are what? Reacting. For instance, if we have, let's say we have calcium carbonate, for instance, okay, if you have calcium carbonate, which is your limestone, in larger particles or in stone as it is, okay, now you will need, okay, let's take chalk for instance. If you take a chalk, a white chalk, and then you want to bring in, let's say, HCl, okay, to react with it. Now, if you take one stick of chalk and then you take another stick of chalk, you grind one of the stick of chalk, okay, and then you leave the other one that is there. Then you take the same amount or quantity of HCl, pour it inside of them in a beaker, okay, and then let's watch what happens. The one that the reaction is going to be fast. You discover that the one that is in powdery form, okay, tends to what? To react faster. You will see effervescence, CO2, okay, giving off there because it's a carbonate. Limestone is calcium carbonate, so it's going to what? Evolve, and then you will see that faster reaction will be faster there compared to one that it is just the stick that was not grounded. This is the reason being that surface area, okay, the one that is in powdery form has a larger surface area. All the particles that make up that chalk actually have contact, okay, direct contact with the what? HCl. So with the shortest time, the reaction is faster. But the one that is just the stick of chalk, you discover that if you pour in your HCl there, it's going to take a while because first it needs to soak in the HCl. The one that are at the outermost part is the one that will get the reaction first. So before it begins to soak in and then begin to what? To react. So which means surface area has a role to play. It talks about the efficiency of the solid soft catalyst, okay, because there's a larger what? Surface area. There's a larger surface area of that particular. So the efficiency of a solid catalyst to increase the reaction rate depends on its surface area. Option B says solubility, where solubility has to do with the amount of a substance that is dissolved in 1 dm cube, okay, of a particular what? Solvent, okay. So the efficiency of that solid soft catalyst is not, don't forget that first we have to what? Dissolve that salt into 1 dm cube first, and before you can be able to say, okay, solubility has taken place, and that one has to do with what? At the particular what? Temperature. So the efficiency of that solid catalyst will not increase the reaction rate here. Then we talk about concentration here. That's when we are looking at it in comparison to what? Surface area. Concentration has to do with the amount also, okay, the concentration, the amount either in molarity of that substance or the what? The mass concentration of that is dissolved 1 dm cube. So which is also just like solubility, and then we talk about the quantity. So the quantity necessarily does not determine the efficiency of it, whether it is small or whether it is much, okay. It is not in the quantity, okay, it is in the what? The surface area, how exposed each of the particles that make up that substance have contact, direct contact with what? With the solvent or the reagent that is coming in contact with it. So we are talking about what? Solid catalyst. So the efficiency of a solid catalyst to increase reaction rate depends on its surface area. So the correct answer is option A. Let's move on to question number 6. Dynamic equilibrium describes a situation where what? Now, when we talk about a dynamic situation, dynamic has to do with a change, okay? Now, when there is a change, a system is already in equilibrium. When we talk about equilibrium, there's forward reaction, there's backward reaction, okay? And according to Le Chatelier's principle, we could have factors that can affect the rate of the chemical equilibrium, okay? A system in chemical equilibrium that is already in equilibrium. If we have changes in temperature, changes in pressure can affect it, changes in concentration of any of the reactants can actually affect that, okay? The chemical equilibrium, a system that's already in equilibrium. Now, when there is the changes in equilibrium, we talk about dynamic equilibrium. When there's dynamic equilibrium has to do with, you know, the rate at which, if the reversible reaction, okay, of the chemical system in equilibrium tends to happen where the forward reaction and the backward reaction happens at the same rate at the same time, okay, we say we have a dynamic equation, dynamic equilibrium. In other words, we are saying when the forward reaction and the backward reaction or the reversible reaction tends to what? To happen or to proceed, to continue to take place at the same rate at the same time. Forward reaction and backward reaction happens at the same time. We say we have a dynamic what? Equilibrium. So let's look at the question. What it says, it says dynamic equilibrium describes the situation where a reaction gives back the reactant. No. Okay, that is just a what? A reversible reaction, but not a dynamic equilibrium. The concentration of the reactant and product is equal. No, that is a chemical system in equilibrium, but that is not what? Dynamic what? Equilibrium. Both forward and reverse reactions proceed at the same rate. Yes, at the same rate at the same time. Okay, so in other words, whether forward and reverse or forward and backward reactions is the same thing. Okay, reverse reactions is the backward reaction. Okay, if both of them proceed at the what? At the same time, yes, then we'll talk about what? Dynamic equilibrium. For option D, reactants are converted to product. No, that does not talk about dynamic. So the correct answer here is option C. Question number 7. The ion that will give a white precipitate with aqueous sodium hydroxide and soluble in excess of the base is what? So among this ion, which one of them, when we talk about this ion now, it means that it is a salt. Okay, that salt, we have calcium present in it. Maybe we have the other negatively charged ion. These are positively charged ions. Of course, these are metals. So which one of them, that if it contains this, the salt that contains any of this metal, if you add sodium hydroxide into it, it will give you a white precipitate. And then if you add excess of it, you have what? You have it dissolved in it or soluble in it. That is what the question is saying. Okay, of course, this is the qualitative aspect of chemistry. Okay, we talk about qualitative identification of salts, of ions, of elements. Now let's move on to the board so that we can have an illustration. So let's say we have, these are 4 different test tubes. Okay, we have, let's say here we have the first one, we have calcium ion here. For the first, the second one is magnesium ion. The third one is zinc ion, 2+, and then we have the copper ion. Okay, now the question says if you introduce sodium hydroxide into it, you add sodium hydroxide first in drop, okay, what happens? Now the same thing, you add the same quantity of sodium hydroxide into this, the same here, sodium hydroxide into this, and then we have the last one here in your copper salt, we have sodium hydroxide added into it. Now what do you discover? This calcium, magnesium, zinc, these 3 of them, if you react them with sodium hydroxide, you are going to have white precipitate. It is very sure of that. Copper, of course, we know copper is associated with, it will give what? A blue coloration. Okay, if you bring in with sodium hydroxide. So what do I mean? If you add sodium hydroxide to this, you are going to have white PPT will be formed. Okay, magnesium, add sodium hydroxide to it, you are going to have white precipitate, which is PPT. And then zinc also, if you add sodium hydroxide, you are going to have white precipitate. So these 3 will give you white precipitate form if you add sodium hydroxide to them in drops. Okay, and then you have sodium hydroxide into this copper ion with sodium hydroxide is not going to give you white, rather it's going to give you a blue precipitate. Okay, because it's going to form, we have sodium hydroxide, we have it in that, we have blue precipitate. So which means that this option D, this last one already is what is eliminated, because this is giving us blue what? Precipitate. So now we have 3 solutions now to do what? To contend with. We have white precipitate, white precipitate, white precipitate. The first test is passed. Now the second one says it is soluble in excess of the base sodium hydroxide. So when you add more of the sodium hydroxide, the first one was in drops, then you keep adding sodium hydroxide, add it to this one. What do you discover? The more you add to it, the volume will just keep increasing. Yet this white precipitate will not be soluble. It will still be what? Insoluble. It will not dissolve in it. Okay, so add excess of sodium hydroxide into calcium ion that form white precipitate, but it will be what? Insoluble. The same thing happens with magnesium. If you add excess of sodium hydroxide into this, of course the volume will increase. Shake it, it is not going to dissolve, so it is still what? Insoluble. So magnesium salt is insoluble in excess of sodium hydroxide, even though white precipitate is formed. But zinc ion, if you add excess of this sodium hydroxide into this, shake it very well, you discover that what? It will dissolve in it. It will dissolve. So we say this is what? Is soluble. Okay, but this one is already off from there. Okay, so which means what? Now this will be soluble because it's going to form complex ion. Don't forget that this falls in the what? In the first transition element series. And then we said transition elements, usually are said to be what? Of course, they have partially filled the electron, this shell, okay, orbitals, even though this one does not meet up because this one has a completely filled d orbital. But in a way, it is still in the same row with that. So it has some characteristics with that. It does not have. So in this form now, it can be able to what? To form complex ion formation. Don't forget that transition metals are said to be what? To form complex ion, okay, when they react. So this one now, it forms a complex ion, okay, when excess of this sodium hydroxide. That is why it is able to what? To dissolve. So it is what? Soluble. So among all of these three now, of course, this one is insoluble because we are looking for what will give white precipitate as well as soluble. So this is giving white precipitate, but it is insoluble. So we eliminate that. So this one will also give white precipitate, but it is insoluble when you add excess of sodium hydroxide. So this also is insoluble. But the last one is what? Zinc here. Zinc is forming white precipitate. In excess of sodium hydroxide, it will be soluble. So which means that zinc ion actually is the ion that will give a white precipitate with aqueous sodium hydroxide and yet soluble in what? In excess of what? The sodium hydroxide. Let's move to the screen so we can choose our answer. So calcium ion is insoluble, white precipitate but insoluble, white precipitate, magnesium insoluble, zinc ion is white precipitate and soluble. Okay, this one is what we give a blue precipitate. Okay, so which means the correct answer is option C, zinc ion. Now let's move on to question number 8. Which of the following pairs of substance will react further with oxygen to form a higher oxide? Okay, react it with oxygen, it forms a higher oxide. If you look at the first option, we have CO2. Okay, if you react CO2 with oxygen, CO2 with oxygen, okay, you are going to have, of course, you will not have, what you are going to have will not give you a higher oxide. Nothing, there's no name that comes like that. If you have CO2 plus O2, maybe you should have CO4. Okay, there's no compound that has that name. Of course, a functional group can actually have that, but no compound can give us that name. So this is not correct. The same thing if you add O2, because if you react further with oxygen, so you react with O2, you have going to have 3 moles of oxygen. So there's no name, okay, but that is well. Even if you add half of oxygen to it, you are going to have H3O. H3O will become ion, H3O positive. Okay, that is not a higher oxide. Okay, that is an ion. So option A is eliminated from this. So we have option B, NO and H2O. So if you add oxygen to this, of course you can have NO2, yes, which is a higher oxide. Okay, but if you add oxygen to this, you cannot have this. So option B is also eliminated. Option C, CO and CO2. Yes, if you add oxygen to this, CO plus oxygen, you can have CO2, okay, yes, which is the higher oxide. But if you add oxygen to this, CO3, no, you can't have CO3. CO3 is not a, but you can have CO3 2 minus, okay, that is a radical, not a compound, not a higher compound, okay, higher, it's not a higher oxide, not an higher oxide, okay, but it is a radical, more of radical. So this also is eliminated. Then let's look at option D, SO2 plus O, of course, will give us SO3, yes, yes, which is correct. We have SO3. Yes, that is sulfur nitrite. Okay, sulfur nitrite. Okay, so that's sulfur 4. So you can have that SO2. SO2 plus oxygen can give us SO3, which is an higher oxide. Then NO plus oxygen can also give us NO2, which is also an higher oxide. So based on that, option D, SO2 and NO are the pairs of substances you can react further with oxygen to form a higher oxide. So the correct answer is option D. Now let's move on to question number 9. The characteristic color of the flame shown when a copper salt moistened with concentrated hydrochloric acid on a platinum wire is put on Bunsen burner. Now, if you get a copper salt, maybe you use a platinum wire, okay, like a loop, kind of. You use it to scoop a copper salt, okay. But that copper salt, before you scoop it, you've added HCl to. Don't forget, reaction is taking place. So you added HCl, okay, into that concentrated HCl to the copper salt first, before you now use a platinum wire to scoop it, and then you put a flame, Bunsen burner flame, and you put it. What color is it going to give? Of course, there's no other color. It's a confirmatory test for the presence of copper, okay. It's going to give us a green color. The reason being that the copper ion that is present there is what gives what? The green light when it is put in a Bunsen burner flame. Of course, don't forget it will be reacted with what? With HCl, concentrated hydrochloric acid, before the reaction can take place. So option A, lilac, green, yellow, brick red. So we have option B. The correct answer is green. Option B is the correct answer. Do you know you can actually take practice questions on our simulated JAMB CBT past questions? All you need to do is to click on the link in the description below that takes you to the Myschool website. There you'll be able to download the Myschool mobile app for your Androids and the Myschool software for your laptops and computers. Please go ahead and start practicing. Now let's move on to question number 10. In the industrial production of hydrogen gas from natural gas, the CO2 produced along with the hydrogen gas is removed by what? Now don't forget that in the process of production of hydrogen, okay, we have at the end product we have CO2 added to it, to that hydrogen gas, okay, because this is CO2 is a gas, hydrogen is a gas, so there's an affinity between them. So first, to be able to separate them, first, of course, don't forget we talk about liquefaction of gases, okay. So first you have to do what you need to do now to be able to what? To isolate, separate this, because this CO2 is an impurity as far as this is concerned, because the mixture is going to be hydrogen gas together with CO2, but we need to produce hydrogen, not hydrogen and CO2 together. So what we need to do is to what? To subject this mixture of hydrogen gas, H2, CO2, this is the mixture, you subject it to what we call PSA, okay, that is pressure gas, okay, pressure steam gas. We have it, we have the pressure, you apply pressure washing, okay, adsorption, we call it pressure adsorption. That is, there's a kind of washing that needs what? You apply pressure to it. All you need to do is to subject this, okay, we call it is a washing under pressure. We call it a pressure adsorption, process. So when you apply the pressure to this CO2 here become absorbed to what? The substance that is introduced, so that thereby it can leave out this what? Hydrogen, and then this hydrogen is what? Is left all alone. So this CO2 is already what? Removed as the impurity. So we call it water or washing under pressure, or we call it PSA, okay. So option A says washing under pressure, yes. Option B says drying over phosphorus 5 oxide, okay. No, you can't do that because it's going to react, okay, with the hydrogen. And then with we have passing the mixture into lime water. You can't do that because if you do that, yes, CO2 is going to be given off, but the hydrogen here, don't forget that this is a mixture, okay. So it's going to affect this, because the lime water, don't forget, lime water is your calcium hydroxide, okay. So hydroxide OH now coming with hydrogen again, you form water, so the hydrogen will not be, so it's not going to react. Then we have using the ammoniacal copper 1 chloride, this will also react. So the best way to what? To separate carbon dioxide from this mixture to form your hydrogen alone is to wash under pressure, which is washing under pressure. So the correct answer is option A. I hope you are enjoying this content. If yes, please don't forget to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we upload our next video. Question number 11. The sulfide, which is insoluble in dilute hydrochloric acid, is what? We have option A says iron sulfide. Well, if you react iron sulfide with HCl, of course, reaction is going to take place there, okay? And then we are going to have a dissolved solution will be formed. So which means that reaction, you will see it. It's a visible reaction. You will see it. So this one, there will be what? A reaction here, because it is what? It will be soluble, because you will see the reaction. Sulfide, iron sulfide is reacting with HCl. Of course, HCl, you are going to have iron chloride, you are going to have hydrogen sulfide eventually. Okay, so there's going to be a reaction here. You will see that it will be soluble, it will be dissolved in it. Now, copper sulfide will not react. Okay, the reason being that by the time you bring in your HCl into this, what happens? There will be no visible reaction. Once you look at it in the test tube or inside the reacting vessel, you cannot see any visible change. Okay, no reaction. So it means that it is what? It is insoluble in it. Now, the reason being that it has a low solubility product. Copper ion is copper sulfide, has a low solubility what? Product. So because of that, it will not react. Add it whether in drop or in excess, nothing will happen. For zinc sulfide will also react with hydrogen chloride. Okay, once you put it, it's going to dissolve into it. It is soluble in it. Then sodium sulfide also, reaction will take place there. By the time you react with it, we are going to have at solubility. That solution will what? Become soluble as you add it into it. So the only one that is insoluble here is what? It is what? Copper sulfide. If you react with dilute hydrochloric acid, it becomes insoluble. Although if you want to dissolve this, you can use a more powerful oxidizing agent. If you use as nitric acid, yes, HNO3. Okay, if you use HNO3, nitric acid is a stronger acid than HCl, so it's going to dissolve this. So the one that can overcome this copper sulfide, okay, that low solubility to boost the what? The solubility level is actually what? HNO3, which is what? Nitric acid. Okay, so but for dilute hydrochloric acid with copper sulfide, nothing will happen. So the correct answer here is option B. Question 12. Which of the following typically represents a photochemical reaction? When we talk about photo, of course, photo means light, okay? Light and then chemical, okay? Photochemical, a kind of reaction that takes place in the presence of light, okay? Reactions between chemicals, okay? Between substances that what? I'll give option A says formation of water from hydrogen and oxygen molecules, yes? Formation of hydrogen and water, of course, H2 plus O2 to give H2O. You don't need light, okay, to carry out that experiment. It's a simple, simple formation, a simple reaction, okay, that does not require a condition for you to bring in light, okay, whether visible light, whether it's ultraviolet light or whatever light, okay, it's not actually responsive. It's not actually requiring that. Option B says conversion of dinitrogen 4 oxide to nitrogen 4 oxide. Okay, dinitrogen 4 oxide, you don't require, I think that is a simple reaction that does not require light also to do that. Option C says decomposition of calcium hydroxide to its oxide. Okay, just decompose. When you decompose, you can apply it to this calcium hydroxide to form what? The oxide of course, we have CaOH2, okay, if you apply it to it, you have calcium oxide plus, then you have the other one being formed there. So this one does not require what? Photochemical reaction. Let's look at option D. We have conversion of silver halide to gray metallic silver. Silver halide to gray convert. We have silver halide. So let's see silver halide. That means halide. That means silver reacting with any of the halogen family. Okay, that is halide. Silver halide. So we can have, let's take chlorine for instance, silver chloride, this is +1, this is -1, okay, this is silver chloride, okay. If you react it, of course, don't forget that it has to do with what? Photochemical. So it requires what? Light energy. And the kind of light that we use, we talk about UV light, okay, that is ultraviolet light. That is the condition with which you can be able to separate this substance. Because don't forget, we are talking about what? A photochemical reaction. So it's going to what? Split this into two, so that we have Ag and then we have Cl2, okay. Yes, it's going to have silver metal and then we have what? Chlorine gas. So let's see, the equation is not balanced. We have 2 of that, so we have 2 here. Okay, then silver is also 2 here. Okay, I think the equation is balanced. This is a gaseous substance. So this reaction will take place in the presence of what? Ultraviolet light. Okay, that is the light energy that will drive this reaction from taking place. So it's a common example. So which means that conversion of silver halide to gray metallic silver, okay, actually will be representing a photochemical reaction. So the correct answer is option D. Question 13. The gas obtained as a product of anaerobic action on organic matter buried in the earth is what? Now, there are two things we will look at here that are very important. Okay, three things. We talk about anaerobic action. Okay, we talk about organic matter, and then we talk about buried in the earth. Okay, so if you get organic matter, when we talk about organic matter, we are talking about waste, okay, that are gotten from plants and animals. Okay, those are organic. That's their derivations from what? Plants and animals. That's organic. Okay, like we talk about organic chemistry. Okay, chemistry of what? Natural products from plants, from animals. We talk about fatty acid, carbohydrates, proteins, and so on and so forth. So we talk about organic matter. Now, if you get your dead plant, for instance, your plant, you've worked and then you bury it underneath in the earth. Okay, you dig a place, then you dump it into it. Organic matter. Okay, now microorganisms will act on it, and then decomposition will take place. Don't forget, we talk about anaerobic. When we talk about anaerobic action, we talk about what? A type of reaction that takes place in the absence of what? Oxygen. Anaerobic. If it is aerobic, that means it took place in the presence of what? Oxygen. So now, once the organic matter is buried underneath the ground, and then there is less or no amount of oxygen that is present there, the microorganism begin to what? To act on those what? On the organic matter that we have in there, and then as they do that, they will now generate a kind of gas that we call biogas. Okay, and biogas, as we know, is a combination of mainly of methane gas, that is CH4, and carbon dioxide, that's your carbon dioxide, which is CO2. So those are the major gases that make up the biogas, okay, that emanated from what? The anaerobic action of microorganism, okay, on the what? Organic matter when it is buried underneath the earth. Biogas is, in fact, that biogas forms what kind of gas that can be used as our cooking gas in our domestic appliances. No, we talk about biogas, okay, that is got, and we said biogas is made up majorly by CO2, which is carbon dioxide or carbon dioxide, and methane gas, which is CH4. Okay, so being that as it may, let's look at the options now. Option A says ethane. Okay, of course, ethane is a gas, but it is not one of the major gases of what? Biogas. We have methane from what? Don't forget, anaerobic action. Methane, which is CH4, yes, is an alkane, which is a gas, of course, which is the major, okay, gas that is present in biogas from this reaction. Option C says carbon dioxide. Yes, it's also one of them. Like I said, it's major, but the major is what? Is methane in the biogas. And then we talk about nitrogen oxide. So these two are part of what? The biogas that is formed when microorganisms decompose or react. Decomposition of organic matter in the absence of oxygen when the organic matter is buried underneath it. But the major that has a larger percentage is actually methane. So the correct answer is option B. Let's move on to question number 14 now. Nigerian crude oil is described as light crude because of its what? When we talk about something being light, it talks about what? The density. Okay, so if we are describing it as light crude, it means that it has a low density. Okay, not just low density, and it has a what? A low sulfur content that is present in that oil. In fact, the sulfur content, a low sulfur content in the oil, Nigerian oil, we are so rich that, I mean, the kind of oil we use, crude oil, or the petroleum we use, is actually having a low content of sulfur in it. Okay, in fact, that kind of oil, we call it sweet oil. They call it sweet. It is sweet because it will not burn, no, like every other one. It will burn so fast that will be causing, havoc to the engine of the cars that are being, or the generators that are used. Okay, it is a sweet oil. So the lower the content of sulfur that we have in the petrol, okay, in the petroleum, the sweeter it is, and then the lighter. So two things makes up for the lightness of the crude oil. We talk about first the low density. Okay, the relatively low density, and then the sulfur content must be low. So those are the two things that make up for the lightness of the crude oil of Nigeria. So option A says low sulfur content. Yes, Let's look at option B, high natural gas content. Well, no. High natural gas content does not make up. Like, remember I mentioned two things. We talk about the low density, and then we talk about the low sulfur content. Then option C says high octane number. Okay, that will be talking about the anti-knocking property. Then we talk about low aliphatic hydrocarbon content. No. So we talk about, among these options now, the best we can go for, if we had a low density, okay, we would have gone for that, but we don't have a low density, but we have a low sulfur content here, which is one of the factors. So the correct answer is option A. Question number 15. An example of aliphatic unsaturated hydrocarbon is what? When we talk about aliphatic unsaturated hydrocarbon, aliphatic means they are straight chain hydrocarbons, okay, that are on the straight chain, okay, not in cyclic form. Okay, we have the long chain hydrocarbon. Okay, we talk about the unsaturated hydrocarbon. When we talk about unsaturated hydrocarbons, don't forget that every hydrocarbons can be grouped into three. We talk about alkane, we have the alkene, we have alkynes. So underneath any of this one, we can have the alkanol, we can have the alkanoic. Okay, those are other functional groups. Okay, but majorly now the hydrocarbons now having the carbon and hydrogen present in them can be alkane, alkene, and alkyne. And then if it is the alkane, let's look at the board. The alkanes, okay, the alkenes, and then the what? The alkynes. Okay, alkane, alkenes, and alkyne. The alkanes, don't forget, they have the general formula CnH2n plus 2. Alkenes have the general formula CnH2n, and alkynes have the general formula CnH2n minus 2. Of course, when your n is 1, for instance, you have a C1H, 2 times 1 will be 2, okay, then plus 2. So that will be CH4. That's the first member, which is what? Methane. So, but what we are going to now is that don't forget that alkanes also, they are carbon single bond. They have single bond with them. That's how we know they are alkanes. The alkenes have carbon double bonds. Okay, and then we have the alkynes having carbon triple bond with them. So that's how we know the alkynes. Okay, and then we know that because these carbon have single bonds between the carbon, okay, we say they are what? Saturated hydrocarbon. If we have 1, 2, 3, 4, 1, 2, 3, 4. So if you bring in hydrogen into all of this, hydrogen, so there's no way you are coming to bring, if this is going to react with hydrogen cannot come here and add up to anywhere here, because there's no bond that is going to break open for this hydrogen to what? To come in here. So this is already what? Saturated. Okay, so for this we have carbon double bond. Okay, now if you are bringing hydrogen to come and react with this, of course we have 1, 2, 3, 4 for this hydrogen. Okay, if you bring in hydrogen to react with this, of course we call it addition reaction. Okay, so this bond can break open. When it breaks open, this hydrogen can now come in. So we now have a single bond here, we now have a single bond here, and then it is no longer complete. 1, 2, 3 for this carbon, and every carbon atom must take 4 bonds. Okay, so this is 1, 2, 3. So this hydrogen, one of this hydrogen, this is H2, will come in here and attach to this, and then the second hydrogen will come in here to attach to this. So now this has become what? Saturated. Now if you bring another hydrogen, it will not have any place to stay here. Okay, so this is what? So originally we now refer, the same thing happens to this. So that's why we refer to carbon double bond and carbon triple bond as unsaturated hydrocarbon, unsaturated what? Hydrocarbon. So in other words, the carbon single bonds are the what? The alkanes are the what? Saturated hydrocarbon, while alkenes and alkynes are what? Unsaturated hydrocarbon. So if you look at the options we have pentane. Option A says pentane ending with ANE. That's how you know the alkanes easily. A, alkanes, pentane. So these are what? Saturated hydrocarbon. Okay, the second option is butanol. Of course, butanol is an alkanol. Alkanol is not, we cannot say it is an unsaturated hydrocarbon because it is already filled. Okay, then we have propene. We have propene here. Propene is having ENE here, just like the alkane, ENE. So this is what? It is what? Unsaturated hydrocarbon. And then we have the last one, which is benzene. Benzene ring is an aromatic bean. Okay, it's an aromatic compound, okay, just C6H6, okay. This is aromatic, okay, not aliphatic hydrocarbon. So among these ones now, the one that is, don't forget, we say the alkene and alkynes are the what? Unsaturated, because the question says an example of aliphatic unsaturated hydrocarbon. So we don't have this one in the options, but we have propene, ENE, which is a member of this what? Of this alkane family, which is unsaturated hydrocarbon. So which means option C. Let's go to the screen. Option A, pentane. This is alkane. This is saturated. Saturated, we have aromatic. Okay, and then this alkanol, then this is what? Propene, which is what? Unsaturated. So the correct answer is option C. Now let's move on to question number 16. Which of the following has an isomer? Which of the following has an isomer? When we talk about isomer, an isomer is a substance, or isomers are compounds, two or more compounds actually, that have the same molecular formula but different structural formula. Their structures, when you draw them, they are different, but the number of carbon that you have there and the number of hydrogen for those compounds, number two or more compounds, okay, actually are the same, but when you draw them, they can look different. Okay, now when we talk about option A says C6H6, of course that is your word, benzene, and benzene is aromatic, so there's no other compound. You cannot have anything. If you have any other thing coming in here, it no longer retains this. For instance, when we talk about C6H6, if you draw that, we have this, okay, this is your benzene ring, okay, so you cannot substitute, of course. This is carbon with one hydrogen. When we talk about isomer, you cannot bring in, if you bring in a compound or a substance to react here, let's say you bring in OH here, okay, and then you remove the hydrogen, this will no longer be, it becomes C6H5OH. In other words, now this one was C6H6, okay. Now this one will be C6H, hydrogen is also C6H6, okay, if you count, but we have oxygen added to it. So because of this oxygen, this and this are not the same, okay, so this cannot be said to be an isomer, okay. Then if you look at the other one, C2H5 in the C2H6 here, in this case now, of course, this is your ethane. If you draw your ethane, let's look at the board, C2H6, we have C2H6 here. So we have carbon 1, 2 carbon atoms, then we have 6 hydrogen, 1, 2, 3, 4, 5, 6. So we have, this is C2. So you cannot change this carbon and say, let me remove this carbon and put here. If you change this carton to be on this point, it stays here. Then you want to draw your hydrogen. The hydrogen is surrounded 1, 2, 3, 4, 5, 6. You end up still having the same thing you have here. So this one automatically also cannot have isomers. The third one is C4H10. C4H10, let's see, we can have 4 carbon atoms. 1, 2, 3, 4. Then we have 10 hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so we have that. So we can decide to change this carbon atom to be on top of this place. So instead of having 4 straight chain, we can have 3 carbon atom chain. 1, 2, 3. Then the 4th carbon, we can decide to put it here. So making 4. Then we draw our hydrogen round. 1, 2, 3, 4, 5, 6, 7. Then we have 8. We have 9. And then we have what? 10. So if you count this now, this one is going to be what we call butane. Okay, that is 1. This one is going to be carbon 1, carbon 2, carbon 3. This is carbon 2. We have a methyl group on carbon 2. So this will be 2 methyl. Okay, the straight chain is what? 3, which is pro. That's propane. Okay, so that's another. So this means if you count the number of carbon here, 1, 2, 3, 4, we have C4. How many hydrogen do we have? We have 10. Count the number of carbons we have here. We have 4 of that. How many hydrogens do we have? We have 10. So the same molecular formula, but their structure, when you draw them, are different. So which means this one, C4H10, can actually have a what? Can have an isomer. Okay, and this isomer are butane and then 2-methyl propane. And the last one is C2H4. Carbon, of course, this is what? This is an alkane. C double bond carbon. So we have 1 hydrogen here, 2, 3, and 4. So you can't change any carbon to stay anywhere. There's no other place it can stay. So this will also not have an isomer. So the only one that can have an isomer here is C4H10. So which means from the options we have option C now, C4H10, option C happens to be the final and correct answer. Question 17. CH3CH2C triple bond carbon hydrogen. This is the compound we're given. So the hybridization in the compound above is what? How do we know the hybridization in this unsaturated hydrocarbon? Okay, let's look at the board. Okay, I have a key notes that we should take note of. Okay, now whenever we have a carbon atom, okay, let me draw out the compound we're given. CH3, we have CH3 single bond, CH2 single bond, C, then triple bond carbon and hydrogen. I hope that's what we have. 1, 2, 3, 4. Yeah. Okay. So whenever we have a carbon atom, okay, with single bonds, like in this case now, to 4 atoms that are bonded to it, we will have sp3 hybridization. Let me say that again. Whenever we have a carbon atom with a single bond, okay, to 4 atoms. When we say 4 atoms, of course, you can draw out this to be carbon, 3 hydrogen, 1, 2, 3, and then we have 4. The 4th one is bonded to this carbon, okay? So whenever we have a carbon atom, okay, that is bonded with, that has a single bond like this, okay, bonded to 4 atoms, 1, 2, 3, 4, we always have sp3. So which means at this point now, between this first carbon and second carbon here, we have sp3 hybridization. Okay, so I'll move on to the second one. Whenever we have a carbon atom with 1 double bond, okay, and 2 single bonds attached to have sp3. Unfortunately, we don't have a double bond here. If we had a double bond here, and then we have the carbon, and then of course this would have been 1 hydrogen here, and then 1 hydrogen here. Okay, if we had double bond here, carbon atom here with 2 single bonds, it would have been sp2. But we don't have that. What we have is what? A single bond. So between here and here we have sp3. So now between here, now we have a carbon atom, of course, single bond here, and then we have triple bond. That's the third one. So a carbon atom with a triple bond, this is a carbon atom with a triple bond, 1, 2, 3, and 1 single bond. This is 1 single bond, triple bond to it. What we have is what? sp hybridization. So I think this will help you remember so far. So we have between carbon 1 and carbon 2, we have sp3. Between carbon 3 and the carbon 4, we have sp hybridization. So these are the 2 hybridization we have. But if we had a carbon double bond, okay, with 2 single bonds, at maybe 1 on this side and 1 on this side, what I mean is this: carbon double bond, okay, then we have 1 single bond here, 1 single bond here to another, atom, okay, maybe hydrogen and hydrogen here. What we have here would have been what? sp2, but we don't have that here. We just have single bond, then we have single bond, triple bond. So here for this is sp and sp2. So we have sp3 and sp hybridization. Let's move back to the screen and see. Option A says the question is hybridization in the compound above is what? We have sp2. We don't even have a double bond carbon here, so this is not correct. sp, yes, we have sp at this point. This point where we have carbon triple bond with a single bond here. This is an sp3 hybridization, but it is not the only two. We still have another one here, so this will not fly. We have sp3 and sp2. Yes, sp3 at this point where we have carbon single bond, okay, with 4 atoms, 3 atoms from hydrogen, then the one is what? 4. We have sp3 there. So but sp2 we do not have there, so this is also not correct. So we have sp3 and sp2. sp3 here at this point, carbon 1 and carbon 2, and then for the 4th, 3rd and 4th carbon, we also have sp here. So we have sp3 and sp hybridization. So the correct answer is option D. Question 18. 1 mole of a hydrocarbon contains 36 grams of carbon. Of course, don't forget when we talk about hydrocarbon, we talk about hydrogen and carbon atom present in there. So, but we're already given that it contains 36 grams of what? Of carbon. okay, and its vapor density is what? 20. The structure of the hydrocarbon is what? How do we know what the structure of the hydrocarbon is? Okay, first of all, okay, let's write down, let's go to the board. We're told that 1 mole, okay, of the hydrocarbon, they didn't tell us the hydrocarbon that it is, contains 36 gram, okay, of carbon. Of course, if it contains 36 gram of carbon, then plus it has to contain what? What mass, okay, of hydrogen do we have left? So we need that because it is hydrocarbon, okay. 1 mole of the hydrocarbon contains 36 gram of carbon and then 8 gram of what? Hydrogen. So all we need to do is we need to know the total mass, the relative molecular mass of the hydrocarbon itself, okay, to give us what we have. Once we get that, we will now subtract this from the total relative molecular mass to get the mass of that. See what I mean by that? The relative molecular mass of the hydrocarbon, okay, should be equal to 36 gram of carbon plus X gram of what? Of hydrogen. Okay, so now the issue is we need to get what? The relative molecular mass of the hydrocarbon. Don't forget that we're given the vapor density of what? Of the hydrocarbon to be 20, and there's a relationship between relative molecular mass and vapor density. Relative molecular mass is equal to 2 times of what? The vapor density. So 2 times vapor density is what gives us relative molecular mass. So in other words, we are saying, recall that relative molecular mass, okay, is equal to 2 times vapor density. So if it is equal to 2 times vapor density, okay, so what do we have? We have 2 times vapor density. We have RMM, relative molecular mass, will be equal to 2 times 20, so which is equal to what? 40 grams. So but don't also forget that number of moles is equal to mass over what? Molar mass. Actually, what we're given here was what? What we're given here was the mass of the carbon, but we are talking about what? Mole. So we have to make this one to get what? The mole of this, number of moles of this, and then we get that, and then we subtract from the total one, then you have what we have there. So number of moles is equal to mass over molar mass. So we are considering for carbon because it was carbon that we were given, okay? For carbon, we are told that the mass of carbon was actually 36 grams. So we'll say this is 36 grams all over. What is the molar mass of carbon? We know that carbon is always equal to what? Is 12 grams. So that 36 over 12, that gives us what? That gives us, that is 3. Yeah, that is 3. So we have 3 moles here for what? Of carbon. Okay, now that we have 3 moles of carbon, now let's look at what we have for hydrogen. Hydrogen is, we have 3 moles of carbon already for that, then we have 40 of that. So if the relative molecular mass of the hydrocarbon is 40, okay, and then we have this to be 3 moles. So we now have, remember that 1 mole of this hydrocarbon should be equal to the number of grams, okay? Since the number of grams here plus this number of grams, the mass of this one should actually give us 1 mole of this. So in other words, the sum of the masses of the carbon and the hydrogen actually should give us the 1 mole of hydrocarbon, should contain 1 mole of hydrocarbon, which is also equal to the what? The relative molecular mass, which is 40. So we can now say that the relative molecular mass of the hydrocarbon is actually equal to the mole, okay, which is this 36 gram of carbon plus what? Plus X for what? Of hydrogen. So relative molecular mass, we got that to be 40 already. So that will be 40 will be equal to 36 plus what? Plus X. So X now, which is equal to 40 minus 36 gives us what? We give us 4. So this is 4 gram, or we can say it is 4 mole, okay? Because it is 1 mole of hydrocarbon that contains this 4 gram of that. So we can say it is also equal to the 1 mole. So we have 4 of hydrogen, then we have 3 of carbon. So in other words, carbon is 3. The molecular mass is going to be, or molecular formula will be carbon will be 3, while hydrogen will be 4. Carbon will be 3, while hydrogen will be 4. So if carbon is 3, hydrogen is 4. So let's try to draw out now the formula. Now let's see. Carbon is 3, so we have the first carbon 1, the second carbon 2, and then the third carbon, since there are 3 carbon here. Then we have 4 hydrogen. If we have 4 hydrogen attached to it, so this first carbon first must take 1, 2, 3, must take 3, that's 1, 2, 3. Okay, then for us to have 4, that means we have 1 hydrogen left. Okay, so we can actually add that hydrogen to this point. This carbon has 1, 2, 3, 4. That's okay, because it must be 4 bonds that carbon will take. Then this carbon has 1, 2, 3, 4. Yes, that's also correct. Then this carbon has 1, 2, 3, 4. Okay, so that means it's correct. So which means we have, this is CH3. Okay, dash. Then we have carbon. Then we have 1, 2, 3. 1, 2, 3 carbon. Then we have this bond. Then we have carbon here. Then we have this hydrogen here. Of course, this is an alkyne. This is a 3 carbon atom. That is a propine. Okay, this should be propine. That is from here. CH3, C, triple bond here, carbon atom. So let's look at the option we have there. Option A says we have CH3, C, triple bond, CH. Yes, of course, that's what we had there. Option B says CH3, CH, CH. No, it is not a double bond. It is triple bond. So this one is eliminated. It's not single bond, this is eliminated. We have CH3, CH3. This one is giving us 1, 2, 3, 4. 4 carbon atoms, and we should have 3 carbon atoms. So it is option A, CH3, C, CH. Yes, so there's a single bond here, or we draw it together, it's the same thing. So the correct answer is option A. Question 19. An emulsion may be produced by shaking a detergent solution with what? Usually when we talk about emulsion, we are talking about 2 or more liquids, okay, that are mixed together to form a mixture, but they are what? They are heterogeneous. They don't mix together, okay? For instance, if you have your oil and water, okay, you can add it together. If you add oil and water, you can form an emulsion with that. But what happens is that in this case now, the emulsion can be produced by shaking what? A detergent solution. So we need an emulsifier. We need something to stabilize, okay, this liquid and this liquid, immiscible liquids, 2 liquids that when you mix them together, they are not homogeneous, okay? They are not completely like like I said, petrol and water, okay? They are immiscible liquids. If you pour petrol on water, you still see the petrol floating on the water, okay? So that will say what? So, but you can have a substance you can add into it that can stabilize that that emulsion. So if you add detergent solution into that emulsion, okay, by what? So if you add it, this detergent solution will help to stabilize that emulsion. So it says option A says palm wine. Of course, palm wine is just your ethanol. You will have ethanol in your palm wine. If you add that into this detergent solution, you cannot produce an emulsion because they are going to mix together, okay? Detergent solution and this. Of course, if you have seen palm wine that is tapped newly, you see it foaming already, okay? So bringing in detergent soap, the solution there is still going to form more solution, so it's not going to produce an emulsion. So option A is actually eliminated. Option B, we have ethanoic acid. The same thing happens. Ethanoic acid is an acid. If you pour it there, you can have the origin is actually from vinegar, okay? If you get vinegar, you pour it into detergent soap, detergent solution, you won't have that because what we just have is an unstable solution. And option C says, so this is also eliminated. We have option C, we have palm oil. Of course, palm oil is a stabilizer, okay? Palm oil, if you add palm oil into a detergent, so of course, when you wash, you can see it. Add detergent into water because you add detergent into water, what happens? Of course, it's going to foam, and then when you add oil into it, it stabilizes it, and then all those foaming you are seeing, you no longer see it again. Everything will go down. It become stable, okay? So that can form an emulsion. So palm oil, of course, you can see palm wine and palm oil. Both of them are palm, but this is oil. This is just wine. You have ethanol here. This one you have oil. So oil is is a product, or it's a substance you can use. A liquid you can add into to detergent solution to get your emulsion. So this, of course, is correct. Option D is water. Of course, this is detergent in water or in solution. So if detergent in solution is already having water in it, so pour water into it, you are not going to have any emulsion. So based on that, the correct answer is palm oil, option C. If you have any question bothering you at all, please feel free to ask from all we have done so far. All you need to do is to click on the link in the description below that takes you to the Myschool website. There you'll be able to ask your question and solutions will be provided within the shortest period of time. Now let's move on to question number 20. The products of the combustion of candle wax are what? You must understand what candle wax is. Of course, candle wax is a type of hydrocarbon, okay? So if you subject it to combustion, combustion means you are reacting with air. Of course, if you light a candle, okay, and then put in the flame and you allow it as it's burning with excess of oxygen, okay, as it burns in air, what happens? There are usually two products that you have. So in other words, what we are saying is that the examiner wishes to know if you actually know what the product of combustion reaction of hydrocarbons are, okay? So but instead of saying hydrocarbon, because they know that if they ask you to tell us the combustion reaction of hydrocarbon, almost everyone knows that it is always carbon dioxide and water. So react hydrocarbon, whether it is methane, whether it is ethane, whether it is propane, whether it is hexane, whether it is decane, whatever hydrocarbon that you react with oxygen, okay, we say that is combustion reaction. And the product usually are always carbon dioxide or carbon dioxide and H2O and water, carbon dioxide and water. So you just need to write your reaction and then you do what? You try to balance the chemical equation. So, but they now say, let us know if you know that candle wax is a type of hydrocarbon. So it takes a student that is smart to know that, oh, actually candle wax is what? Is a type of hydrocarbon. So I will just write on the board an equation to show the reaction between hydrocarbon and oxygen burning in it. That's the combustion reaction. So if we have C, okay, I'll just say CXHY, okay, reacting with oxygen, which is burning in air, you will always have CO2 plus what? H2O. So in other words, all your carbon atom that you have here will be formed here. So I'm going to have here X here, okay? Then all your hydrogen that you have here will be formed in this water. So I will just have Y here to show that all the carbon you have here should be formed here, and then all the hydrogen you have here will eventually be formed here. So in other words, let's say we have C. Let me use methane, CH4 plus O2, okay, to have this. So this is going to be, of course, we must have CO2 and then we must have H2O. So we just need to balance. We have one carbon here, carbon atom here, 4 moles of hydrogen here, 4 hydrogen here, we have 2 here, okay? So which means for it to be 4, this must be what? Must be 2, okay? So in other words, all the carbon you have here, like I said, is here, but necessarily it won't be the same value. But all the hydrogen you have here must be formed in your water. All the carbon you have here must be formed in your carbon. That's an easier way to help you balance this equation so you don't waste much time. So all the carbon we have here must be formed here. All the hydrogen we have here must be formed here. So hydrogen is 4 here. So hydrogen is 2 here. So add 2 here to 4. So you just balance it up now. So hydrogen is 4. Oxygen here is 2 here plus 2. That is 4 oxygen. But you have 2 here. So if you put 2 here, you balance it up. So the same thing happens if you have C2H4. Okay, let's say C2. Let's say we have C2H6. Okay, plus oxygen. Combustion reaction. We must have CO2. Okay, because this hydrocarbon, CO2 plus what? H2O. So like I said, all the carbon you have here, 2 of that, you must reciprocate here. So 2 of that, 2 here. Then hydrogen, we have 6 hydrogen here. We have 2 here. So put 3 here. It is balanced up. Okay, so I think that's easy. So you now balance your what? Oxygen. Oxygen here, 2 times 2. Here is 4. Oxygen here is 3. So 4, 3, that is 7. So we have 7 here. So you can have this 7 over 2. Can do it because 7 over 2 times 2 will give you 7. So it is balanced up now. So in other words, hydrocarbon reacts with oxygen to form what? Carbon dioxide or carbon dioxide and water. Let's move on to the board, to the screen and see what we are. Option A says hydrogen and water. No. Option B says oxygen and water. No. Option C says carbon 4 oxide and water. Yes, CO2 and water. That is usually the product of combustion reaction of hydrocarbon. The candle wax hydrocarbon. So option C is correct. Option D says carbon 2 oxide and water. No, it's carbon 4 oxide. You will get carbon 2 oxide if it is controlled, okay, it's not when the air is not in excess, okay, when you have little amount of air, regulated amount of air, okay, then the burn, what is called, the candle wax begin to burn, not complete combustion now, okay, it is an incomplete combustion because you have limited supply of air. So that's when you now discover that when the candle is lit, you'll be seeing that the room is filled with flame. You can have more of the soot. Those flame you're having is the soot. You smoke them and you bring them in, it is poisonous. That is your carbon 2 oxide, okay? So when you have them, you can touch it, you can form, oh, this is soot like coal, okay, that you have there. But that is what incomplete combustion, okay? In the presence of what limited supply of air. But this one now, for complete combustion here of candle wax, we have carbon 4 oxide and water. So the correct answer is option C. Do you have better steps or better explanation to all the questions we have treated so far? Please feel free to share with us. All you need to do is to go to the comment section, indicate the question number and the solution you wish to share. Let's move on to question number 21. When 50 cm cube of a saturated solution of sugar of molar mass 342 gram at 40 degrees Celsius was evaporated to dryness, 34.2 gram of dry solid was obtained. The solubility of sugar at 40 degrees Celsius is what? We need to solve out this. Let's move on to the board. First, we're given, like I usually say, I subscribe and I tell my students and minders that ensure that you write out the given parameters in every calculation that you want to solve. So it will help you to know what you actually want to see, the relationship between what you are given and then the unknown that you wish to say. So we're told that when 50 cm cube of a saturated solution, so volume is equal to 50 cm cube, okay, of sugar for when 50 cm cube of a saturated solution of sugar of molar mass 342. So we have molar mass of the sugar is equal to 342 gram, okay, at 40 degrees Celsius. So we say temperature is given at 40 degrees Celsius. Please take note, solubility will take place at specific temperature. There are temperatures at which it takes place, it's a factor. So was evaporated to dryness, 34.2 gram of dry solid was obtained. So that is the mass, okay? Mass of solute was what? 34.2 gram, okay? Was obtained. The solubility of sugar at 40 degrees Celsius is what? So we're asked to find what? Solubility of the sugar. So we have that as question mark. So what is the relationship between this now? We have volume, we have molar mass, we have mass of solute. Okay, so we can say the definition or the formula for finding solubility is actually equal to number of moles of solutes, okay, of solute, that's your salt or the sugar in this sense now, multiplied by 1000 divided by volume, okay, volume of the solvent, okay. In this case now we have solution given, the volume of the solution. So solubility is equal to number of moles of solute times 1000 over volume of this. That is the formula for finding solubility. But in cases where we are not giving number of moles, maybe 0.5 moles of sugar, what we were given was mass and molar mass. You remember that number of moles is also equal to what? Mass over molar mass. So in place of this number of moles, we can replace with what? Mass over molar mass. Okay, if you are not giving number of moles, so we can say solubility is equal to mass over molar mass. So in place of this, then times 1000 divided by volume. So any one of these would serve. So it is number of moles. Of course, if you ask to define solubility, you just say solubility is the number of moles of the solute that is dissolved in 1000 cm cube or 1 dm cube, okay, of the what? Of the solvent, okay? Of the solvent. So that's what we have there to form a solution. That's solubility definition. So number of moles here, we're not given, but we're given molar mass. We're given mass and given molar mass. So we can use, in place of number of moles, mass over molar mass times 1000 over volume. So let's see what we have. The mass is actually what? 34.2 gram. All over, what is the molar mass? It is 342 gram, okay? Then multiplied by, we have 1000. All over the volume actually of the solution is 50 cm cube. The values actually are intentional, okay? We see that they have something that's common. So we can solve this with a calculator, but if you have a calculator, you can punch it and write your solution there. So for me, I don't have a calculator, so I'll just solve it by heart. So I move this point once. Because I'm moving this point once, this one, the point is here. So I move this once, so I will add 10 to it, okay? So that what I have now will be 342 all over 3420, okay? Then we have times 1000 over 50. So 342 goes here 1. 342 goes here 1, but there's 0 here, so I add it to it, making 10. Okay, so 10 goes here 1, 10 goes here, that 0 cancels 1 0, so I'm left with 100 over 50. 50 here 1, 50 in 100, that is 2. So my answer is 2.0 mole per dm cube. So that's the solubility of the sugar at 40 degrees Celsius. Let's move on to the screen and see option A. Fortunately, it's just 2.0 mole per dm cube. So the correct answer is option A, 2.0 mole per dm cube. Question number 22. Which of the following results in the fall of acid rain? We've often heard of acid rain, acid rain, acid rain. What actually is acid rain? How are they formed? Now, acid rain, usually when we have pollutants, okay, in the atmosphere. Pollutants in the atmosphere usually like sulfur dioxide, sulfur 4 oxide, and oxides of nitrogen. We call it NOx, okay? We have NOx, sulfur dioxide, SO2. We have oxides of nitrogen, NOx. NOx, the X means that it will actually be NX, could be maybe 1, could be 2, could be, okay, it could be 1, it could be 2, whatever. So that's oxides of nitrogen. So when any of this one now actually reacts with water and oxygen, these are found in the atmosphere, okay, actually, so as particulate nature, as pollutants, okay. So once they react with oxygen and water, okay, then it will now react to form acidic oxides. So when it forms those acidic oxides now, it will now fall down and now form what we call precipitate. So once it precipitates down and falls down as rain to form what we call acid rain, okay. So oxides of nitrogen and sulfur 4 oxide usually will form acidic rain when it reacts with water and what? And oxygen, okay, that we have, then we form that. So option A says oxides of lead. No, we say oxides of what? Nitrogen, because oxides of lead, if you react it with water and oxide, it's not going to form acid, okay. We have, because this lead actually is not any of this one, and we can have it also as oxides of carbon. So we have particulate matter. Yes, particulate matter usually could be said to be, just like we talk about, these ones are particulate, but we can have soot from carbon monoxide. Okay, we can have some other particulate matter. So generally that is, but it's not all particulate matter actually that reacts or results into what? To acid rain when they react with oxygen and water, okay. So that being that it has a limitation, we have oxides of sulfur, okay, we already said that's SO2, we can have SO2, we can have SO3, so it can be SOX here, so which means option C, oxides of sulfur, is one of the compounds, the pollutants in the atmosphere that can actually react with water and oxygen to form acidic oxide, which form a precipitate to fall down as acid rain, okay. And option D says gaseous hydrocarbons. You can have more hydrocarbons. If you have hydrocarbons, reacting with oxygen and water, of course, you are not going to have an acidic rain, okay. Most substances that form acidic rain, okay, will actually give rise to acidic oxide when they react with oxygen and water, okay, they are pollutants in the atmosphere. Okay, so we talk about oxides of sulfur, oxides of this. So more likely it is what? Oxides of sulfur. So option C is the correct answer. Question 23. Water has the ability to dissolve almost all substances because its molecule has a structure with what? This is what we call universal solvent. Okay, we refer water as a universal solvent because it has the tendency to dissolve so many substances. Okay, in fact, most substances compared to other solvents. Okay, that you can have maybe ethanol and other ones. So the reason for this is just because of the polar structure. Okay, polar structure of the water. Now, water has what we have the polar structure, we have the positive side and negative side of the polar. Of course, you know that in water we have H2O. If you dissociate H2O, we have hydrogen positive, H plus, and then we have OH minus. Okay, so usually hydrogen is bonded to one oxygen, okay, in the middle, and then the oxygen is bonded to what? Another hydrogen. Okay, so we have HOH there. So there is a dipole, there's a polarity, okay, of those of the kind of atoms of the structure of that water. So because of that, it can attach easily, okay, to substances. It tends to dissolve. So when it reacts with them, it comes in contact with them, it breaks off those bonds, and easily it's able to dissolve those substances with it. So it has the polar structure. That is what is responsible for it to become a universal solvent. Option A says one positive end and one neutral end. No, if it is one positive and one neutral end, it's not going to be, it's not going to be polar. Okay. Option B says one positive end and one negative end. Of course, yes. One positive. I said we have hydrogen positive, we have OH negative. So we have one positive, one negative, and then option C we have two negative ends. No, this will not be an option D, two positive ends. No, it's not two negative, it's not two positive. One positive and one neutral, and it should be one positive end and one negative end. So the correct answer is option B. Question 24. When a crystal was added to the clear solution of its salt, the crystal did not dissolve and the solution remained unchanged. This shows that the solution was what? So what it simply means is that you have a salt, okay, already dissolved in a solution, in water or in a solvent, okay, and then when it was dissolved, you now get more of the crystals of that particular salt. Then you pour it into that solution already of that salt. Then you discover that it was just there looking at you. Nothing was happening. It was not dissolving. It was just the way it was when you pour it in. What it simply means is that the salt, okay, the solution has already been saturated because all the amount, it has taken the maximum amount of what? Of salt, okay, of solute that it can what? It can dissolve. So if you add more, it will just be there, it will not dissolve. But if it still have space, so in other words, we are saying that for us to have solution, we have solvent reacting with solute to form solution. So if, and there is an amount of, solute that a solvent can actually dissolve, that it can take, that it can accumulate. So if you are taking more of the crystal of that salt now, you are adding it into the solution and then it is not dissolving. So it's simple. It's simply meaning that the solute or the solution has reached its maximum amount of salt that it can dissolve. It has taken it. So if you pour more crystal, nothing will happen. So it means that the solution has been what? Has been saturated. Okay. Option A says supersaturated. Option B concentrated, unsaturated, saturated. So the correct answer is option D, saturated solution. Now let's move on to question number 25. A particle that contains 11 protons, 12 neutrons and 10 electrons is probably a what? Neutral, non-metal, metallic ion, non-metal. Let's go to the board and demonstrate that. A particle that contains, so let's say let the particle be what? Be X, okay? We're told that the particle contains 11 protons, so I can say number of proton is actually 11. Then number of neutrons is actually 12. And then we say number of electrons is actually what? Is actually 10. Okay, so we want to know what type of substance, okay, particle is this X. So let's start with number of proton 11 shows that the number of proton is actually what? The atomic number, okay? So atomic number of proton is the same thing. So we write here 11. So number of proton is 11. It means that the atomic number is what? Actually what? 11. So we have number of neutrons 12. So don't forget that down here we write the atomic number. Up here we have what? Mass number. And mass number is usually what? The number of proton plus what? Plus neutron. Atomic number is what? Number of proton alone, which is, that's why we wrote 11 here. Number of proton is atomic number. But mass number is addition of proton and neutron. So if you add up proton here 11 with neutron here, that should give us 23. So here is 23. So of course, you should know what element this is. This is sodium, because sodium is what? Atomic number 11 and the mass number is that. So, but that is not our area of this. Now, we now have number of electrons to be 10. Now, listen. If number of proton and number of electron were equal, were the same, this would have been a neutral atom. Okay? When number of proton and number of electron are the same, this would have been a neutral atom. That is, when we say neutral atom, there will be no charge that will be here. It will just be like this, because for a neutral atom, number of proton is always equal to number of what? Of electron, because the competition is always between proton and electron. Two of them would have the same thing. But in this case now, number of proton is more than number of what? Electron. So the competition is usually between proton and what? And electron. So the proton now says, oh, I have 11. I am 11 years older. And then electron says, oh, I am 10 years older. And then proton says, oh, I am by 1 older than you. So if I am by 1 older than you, and don't forget, so which means that we are going to have what? 1 here. Okay? Proton says, I am by 1 older than what? Electron. So it comes here. And don't forget, what is the charge of proton? Charge of proton is what? Is always positive. While electron will be what? Negative. So proton will be positive. That will be what? Positive, because it is proton that is by 1 more than electron. So it will be positive here, plus 1. And then electron will be what? By 10. So it is by 1 more than this. So this will be positive. But if it is in a case where we have number of protons, let's say we have number of protons to be 10, and then it's number of electron that is 11. So what this simply means is that electron will say, oh, I am by 1 more than what? Or older than proton. If I am by 1 older than proton, so which means that what? Electron is going to be the one that will be here, because electron is negatively charged always. So that will be what? Minus. So minus 1. But we don't write minus 1, we just write minus here. So this would have been, and you know that it is what? Non-metals usually that are what? Negatively charged. But in this case now, plus 1 or just plus is what? Is the proton that is what? Positively 1. So, and we know that it is what? All metals. Okay? Metals are always what? Positively charged. So this is a metallic ion, while this one is a what? Non-metallic ion. It means that what? Electron is more. But in this case now, positive. So positive one means that what? Metals are plus 1, so they can give out 1 electron. So in this case now, it is positive 1. So this is what? A metallic ion here. That's what we had from the question. Positive. So that is metallic. So let's go back to the screen. Option A says we have neutral non-metal. That's not a non-metal because the charge we had there was non-negative. So option, of course, it says neutral. If it were neutral non-metal, okay, it would have been just X. 11, 23. There will be no charge here because number of proton would have been equal to number what? Electron, okay? But it's not neutral. The option B says metallic ion. Of course, do we have a positive charge there? Yes. Once you have positive charge there, it means it's one metallic. So option B is correct. Option C says non-metallic ion. It would have been non-metallic ion if we had a negative value here. Yes, it would have been non-metallic ion, and it would have been neutral metal if there is no charge at all here. So the correct answer is metallic ion. Option B is the correct answer. I hope you enjoyed this content because I really did solving these questions. If yes, please don't forget to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we upload our next video.